Hello, we're back with number 6 on the practice exam. It's dealing with LTI system properties. We are asked to state the causality and stability conditions for the impulse response. So we have the conditions written right here. For continuous time, the condition on the impulse response for causality is that h of t must equal 0 for all, that's what that little upside down a means, t less than 0. The stability condition is that the integral of the magnitude of h of tau, where we've made a variable substitution, just t for tau, tau for t, the magnitude of h of tau from negative infinity to infinity, it must be less than infinity. So for the discrete time, the conditions are analogous. We have the condition for causality is going to be h of n must be equal to 0 for all n less than 0, and the stability condition is that the summation of the magnitude of h of k from minus infinity to infinity is less than infinity. So you should have these conditions written down on your cheat sheet, unless you've committed them to memory. But I don't really think there's much value in committing them to memory. So just write them on your cheat sheet. So A is, we're given the impulse response h of n is equal to 0.9 n u of n plus 1. So causality is straightforward. We just need to test a value of n less than 0 and see if we get h of n equal to 0 for that value. So we'll try -1, h of -1 is equal to 0.9 minus 1 times u of -1 plus 1 equals 0.9 minus 1. U of -1 plus 1 is u of 0, so that's equal to 1. And we can write this as 1 over 0.9, and whatever that is not equal to 0, so the system is not causal. Okay, now we need to test for stability. Sorry, my screen didn't seem to be moving. So we go back to the condition for stability, and I'm going to put that in. So start from k equals minus infinity to infinity, the magnitude, point n, k times u of k plus 1. And if this summation is less than infinity, the system is going to be stable. So we need to get this in a form that looks a little more similar to something we know how to handle. Something we know how to handle is the geometric series for the bounds starting with the lower bound of 0. The infinite geometric series is a little more difficult to handle because we have a negatively powered series then, and that's just not something we're going to deal with. So I'm going to pull a little trickery here. So we're going to say that our new bound I is equal to k plus 1. And that means k is equal to I minus 1. Okay, so the reason we wrote it like this is because we have this u of k plus 1, and that's really inconvenient for us because we don't have any way to handle this unit step function the way it's written in a convenient fashion. So we want to get rid of that shift. So now we can write k is equal to minus infinity. So then our new lower bound I is just going to be equal to k plus 1. The lower bound k is negative infinity, so negative infinity plus 1 is still negative infinity. Our upper bound I is going to be infinity plus 1, and infinity plus 1 is still infinity, so that doesn't change anything. And we can also note that our function is always positive and it's not complex either, so our magnitude is just going to go away. So now we can write point n, 0.9, and k is equal to I minus 1, and then we get u of I. Okay, so our unit step function is non-zero for values of I greater than 0. So for the iterations of I equals negative infinity to I equals minus 1, this resolves to 0. So we can move our lower bound up to 0. And our upper bound stays the same, it's just infinity. So now we have 0.9 times I minus 1 times u, and we can get rid of the u of I, because for I greater than 0, it's just equal to 1. So now we can say that 0.9 I minus 1 is equal to 0.9 times 0.9i times 0.9 minus 1, and this is a property from algebra. So now we can write, and just to be clear, that property is I'm not sure of the exact name of the property right now, unfortunately. I believe it's just the property of exponents. So now we can write I equals 0 to infinity, and we have 0.9i, 0.9 to the negative 1 is just 0.9, so we get 0.9 times the summation I equals 0, infinity, 0.9i, and now this looks like something we've covered in this class. That's the geometric series, which is and this is true on the condition that the absolute value of a is less than 1. In our case, we have 0.9, so that's definitely less than 1, so this just resolves to 1 over 0.9 times 1 minus 1 over 1 minus 0.9. And whatever that is less than infinity, so this system is stable because our condition was that the summation had to be less than infinity for the system to be stable, so our condition was met. And this is obviously pretty easy to figure out what that is, but remember, on this midterm, time is of the essence, and you want to be as efficient as possible. So our condition was only that it had to resolve to be less than infinity, so it doesn't actually matter what this is. So that's why we're not even going to worry about finding the actual value. Okay, let's go to B. B is in continuous time. H of t is given as e to the minus 3t u1 minus t. You can write that like that. Okay. So for causality, h of t must be equal to 0 for all t less than 0. So we can just put in, say, h of minus 1, that gets us e minus 1 times minus 3 is 3, times u of minus 1 is equal to 1 plus 1. That's equal to e3 times u of 2. So u of 2 is just equal to 1. So e3, whatever that is not 0. So this system is not causal because we get a non-zero value. And our condition for causality was that all t less than 0 must be must have the impulse function resolve to 0. Okay, so now let's check for stability. And that condition had us taking the integral from minus infinity to infinity of h of tau d tau, the magnitude of h of tau, and if it's stable, this integral must be less than infinity. You could also say it has to converge to some value. Okay, so let's figure out what this function actually looks like. Because we're going to split this integral into two. So this is going to be the tau axis, and h of tau is equal to e minus 3 tau times u of minus tau plus 1. Okay, so this is, as always, when we're doing a transformation like this, we're going to shift the function first. So this is u of tau plus 1, and this is u of minus tau plus 1, because we just reflected this graph. So now we can see this is our final graph. We can see that this integral is going to be non-zero for only values less than 1. So we can break this integral up like this. Minus infinity to 1 times h of tau d tau plus 1 to infinity, but we just said the unit step is 0 for values greater than or equal to 1, so our integrand is clearly 0. And the integral of an integrand that's 0 is just 0, so we don't have to worry about that. So now we can write, finally, and from negative infinity to 1, the magnitude of our unit step is just 1, so we don't even have to worry about that. We just need our decaying exponential. Clearly that's always positive, so we can get rid of the absolute value. That's equal to minus 1/3 times e minus 3 tau minus infinity to 1. So this is equal to minus 1/3 times e minus 3 minus e minus infinity, and e minus minus infinity is just e infinity, because the negatives cancel. And we know that any number minus infinity is going to be negative infinity, but we have this negative out here, so we get, if we distribute that, we get positive infinity. And that is equal to infinity. So our condition for stability is that the integral had to resolve to be less than infinity, so this system is not stable. Okay, that's number 6, and I'll see you in the next one.